Hello everyone. In the previous lecture, I had mentioned that although we were able to formulate a theory for torsion uh, for non-circular cross sections even, but we would still like to go for a kind of theory which would allow us to address various problems given a certain geometry instead of guessing the solutions. And the way that we go about doing it is to use the what was actually given by uh, Ludwig Prandtl, which later came to be known as the Prandtl stress function. And please note that this is the same Prandtl who gave us the boundary layer theory. All right, so as the name suggests, it is a stress function that we will be looking at, and much in the same way that the Airy stress function was presented with the motivation of satisfying the equilibrium equations, here also the motivation is somewhat alike. So what we say is that uh, the stress components sigma xz and sigma yz, uh, they will be represented through these expressions. Twice g, where g is the shear modulus. Alpha is the same alpha that we had been discussing in the previous videos. That is the twist per unit length. And this psi that we are looking at here, that is what is the stress function. Sigma yz is equal to minus twice g alpha del psi del x, and the underlying motivation for considering these kinds of expressions is to just ensure that the third component, that is the z component of the stress equilibrium equations, that gets satisfied. So del sigma xz del x plus del sigma yz del y, that should be equal to 0, where we note of course that sigma zz is equal to 0. Okay, so given all the kinematical hypothesis that we had already discussed in the previous lectures, the sigma zz will turn out to be equal to 0. Otherwise, if this had not been 0, then we would have an extra term here like plus del sigma zz del z. Okay, but we don't have to worry about it now. Okay, so what happens is that if you actually substitute this expression here and this expression here, you will see that this becomes a 0 equal to 0 form. So this is exactly the same kind of things which we had seen in the case of the Airy stress function also, but there our motivation was to satisfy the x and y component of the stress equilibrium equations. All right, now that we have these two expressions of sigma xz and sigma yz, what we would like to do is develop some kind of relation between these two expressions and what we had from earlier, meaning to say that if we just go up, so we have these expressions for epsilon yz and epsilon zx. All right, so let me just copy these. So the epsilon yz and the epsilon zx, so this is our epsilon yz and this is our epsilon zx. And please also note that this kappa, if you just look back up, so what we had said was that this kappa here, that is equal to alpha phi. Okay, so we are going to use that. That's it. So what we are going to end up with here is that sigma yz, so I can make the change here itself, sigma yz, okay, maybe I'll not be too much lazy, I'll just write it again. Sigma yz is going to be equal to twice g epsilon yz, which means that I'll have g alpha, I'll take the alpha out of this bracket, x plus del phi del y, and sigma zx or sigma xz, that is twice g epsilon zx, so I'll have g alpha minus y plus del phi del x. Okay, so all that I need to do is compare this expression for the sigma zx or sigma xz with this expression, and this expression for sigma yz with this. So therefore I'll have minus twice g alpha del psi del x from here will be equal to this thing, alpha g alpha x plus del phi del y, so that I actually end up with minus twice del psi del x is equal to x plus del phi del y, and from this one I'll have twice g alpha del psi del y, that will be equal to this thing, that's g alpha minus y plus del phi del x, so that's twice del psi del y is equal to minus y plus del phi del x. Okay, so what I want to do from here is I want to eliminate the phi. Okay, and the way that I'll do it is to take the del x of this entire equation, and from that subtract the del y of this equation. The motivation here of course is to obtain a del square phi del x del y here, and to obtain a del square phi del x del y here, so that these two things will get eliminated. Okay, so let me just take these terms to the next page. Okay, let me adjust it a little bit. So from these two, what I will obtain is minus 2 del square psi del x square minus 2 del square psi del y square, and when I take the del x of this in that equation, I'll get a 1 over here, and when I take the del y of this second equation, I'll get a minus 1 over here. So when I subtract these two, I will end up with a 2. So overall I end up with minus Laplacian of psi is equal to 1, or I can change that, del square psi is equal to minus 1. So that is the equation in terms of the Prandtl stress function. So let me box that. It's a very important equation, and it is kind of the counterpart of the Laplacian of the phi equal to 0 equation which we had obtained earlier. So what I mean to say is that this equation that we had obtained earlier, it is kind of the counterpart of that equation in terms of the Prandtl stress function. Okay, so next, what about the boundary conditions? Well, we have the zero traction boundary condition on the outer surface of the shaft. Okay, so we use the no traction boundary condition on the outer surface of the shaft So what I mean to say here is that if I just go back to this first diagram, this curved surface covering the entire length of the shaft, that surface is entirely free of traction. Okay, so on that surface I'll have the zero traction. Okay, so that will be given by sigma xz nx plus sigma yz ny equal to 0, and in terms of the Prandtl stress function, that is going to give me twice g alpha del psi del y, and let us not forget that this nx is nothing but dy ds, and this sigma yz is minus twice g alpha del psi del x, and this ny is minus dx ds. So what we are going to obtain from here is, we can just cancel out this twice g, we can also get rid of the alpha, so what we are left with is d psi dy, dy from here, we remove this, get rid of this ds, plus this minus and this minus is plus, and this should be a partial derivative, sorry about that. Plus del psi del x dx is equal to 0, and that is nothing but the differential of psi. Okay, so d psi, where psi is a function of both x and y, that gets expanded out using the chain rule as del psi del x dx plus del psi del y dy. So we have just gone the reverse way and written this as the differential of the psi. Okay, and that is equal to 0. What that implies is that the psi is a constant on the periphery of the shaft. Okay, is a constant on the periphery of the shaft. So on the entire cross section, if you just consider the cross section again, on this entire periphery, this psi is a constant. Now if you had been wondering all along that how this using the Prandtl stress function actually helps us in addressing problems given a certain geometry, this is the missing link. Okay, that because the psi will be a constant on the entire periphery, so given a certain geometry, all that we need to know is the equation which defines this periphery, and we can utilize this this condition that this Prandtl stress function is a constant on the periphery to obtain an expression based on that geometry. And through the examples that we'll be doing, we'll see how that can be very, very easily done. Okay, so Another very important thing to note is that because this is a constant and because the only connection that this psi has with the stresses is through the derivatives, then it really doesn't matter if we can add or subtract certain constants from this. Okay, so we'll exploit those things later on while addressing the various examples. But for now, what I want to do is, you see, we are going kind of neck to neck with the theoretical framework which we had developed in the previous videos, meaning to say that we had obtained a governing equation in terms of the warping function phi, and here also we have obtained a governing equation in terms of the Prandtl stress function psi. Earlier we had obtained a governing or a boundary condition in terms of the warping function phi, and here also we have obtained a kind of condition involving the Prandtl stress function on the entire boundary. But what is missing, however, is the connection with the torsional rigidity, which we have not talked about. Okay, so remember that earlier we had obtained three conditions or three equations. So let me just go back and show you that. You see, we had these three boxed equations. So what we would like to do is to obtain the counterpart of this. Okay, basically we want to have an expression involving the torsional rigidity in terms of this Prandtl stress function. Okay, so how do we do it? Well, the torsional rigidity, as I had mentioned in the previous lecture, is given by this Gj, and if we just take a look back, this Gj was like this. Okay, so this was this basically I mean the G is simply the shear modulus. The only thing involving the only thing that we need to note here is this expression for the J. So what I will do is I'll just copy this thing. Okay, so now what I would like to do is simply replace these expressions involving the phi with those involving the psi, and for that all that I have to do is just take a look back at the previous page where I have this thing. The del phi del y can be expressed in terms of the psi like this. It is minus 2 del psi del x minus x. So that's it. And for the del phi del x, what I have is twice del psi del y plus y. All right. So if I just simplify that a little bit, let me not forget this this G, which is present on the left hand side. So I have this minus twice x del psi del x minus x squared minus twice y del psi del y minus y squared. So this x squared cancels with this x squared, this y squared cancels with this y squared, and what we are left with is this minus twice g x del psi del x plus y del psi del y. So as we have done so many times earlier, we are going to go forward with the motivation of using the Green's theorem, and for that we'll just absorb this x within this partial derivative with respect to x, and this y within this partial derivative with respect to y, and let's see what we obtain. So del x of x psi minus, so this is basically del x of x, which is just 1 times psi, plus del y of y psi minus del y of y times psi, so that the del y of y is just 1. So we have this, and please note now that this this particular combination del x of something plus del y of something is where we get to use the Green's theorem, so that considering this term and this term, what we are going to end up with is x psi n x plus y psi n y. So this is a cyclic integral over the periphery, and for this, whatever is left here, that is going to give us 4g. So we have a twice psi here, minus twice psi, that minus comes outside, that gives me the plus, so 4g psi dA. All right, so it seems a rather inconvenient looking expression, but we'll see later that this can be further simplified. Okay, this can be significantly simplified, but for now we'll just keep it as it is here. Okay, as we consider the different situations, especially to do with singly connected domains and simply connected domains and multiply connected domains, we'll carry out the simplifications. All right, so basically what we have managed to do is to obtain the equations corresponding to the ones that we had obtained earlier involving the warping function, but this time involving the Prandtl stress function. And please note that unlike the approach that we had been doing in the various chapters earlier, and even in this chapter, we did not really proceed by any variational route. Okay, that's a major difference from earlier. Rather, we just took, I mean, it was more like an exercise in applied elasticity, which we had done in our previous semester. But no matter, our objective has been realized of obtaining the equations, the corresponding equations in terms of the Prandtl stress function. And as I have emphasized in the previous page, that because we have in our hand now the condition that the psi is a constant, this very important condition that the psi is a constant on the periphery, it directly gives us a recipe of connecting the given geometry to the solution procedure. All right, on that note, I'll end this video. Thank you very much.